So I had a couple things on deck that I thought I'd talk about today. Some more about just syntax, that pesky asterisk, especially when it comes to returning values from functions and returning pointers from functions. Talk about that a bunch. Uh, the pointer exercise has a bunch of string manipulation in it. And so another thing I could do there is we can go through a bunch of string manipulation functions that aren't in there. I dropped some code in the channel yesterday for calculating string length, but we could rewrite stuff like string length and other string functions that are in the standard library but aren't in the assignment. So we could do that. I have a note here. I could talk a little bit about the heap and the stack, but I'm also open to suggestions, or especially to start questions that have come up. One vote for that stuff. Does anybody have any questions that came up when they were tackling this stuff yesterday that we could talk about first? The poll seems to have pretty decent confidence in pointers, so that's good. Maybe there aren't any questions. Or maybe there aren't any questions that don't sound like they'll be addressed by what we're about to talk about. How do we access substrings? Question about that substring problem. Yeah, let's see here. Let me think if I can come up with a good example for that. That doesn't give away the answer. I think I can. What is that? Actually, what is that thing in the assignment? Let's see, pointers. Find string. Yeah, I can probably do a little hinting about how we access substrings. All right. Cool. Before we do that, let me talk about some syntax again, just to get that back in our minds. Let's see. Where should I go? Let me bring up VS Code this time. Even though it runs horribly slowly when I'm recording, it does have that nice terminal window for doing builds. So let's see here. All right. What should I start with? Oh, that syntax thing. I wanted to, let's see, how should I talk about this? We haven't gotten to malloc yet. So I'm going to talk about this kind of generally, and then hopefully some future code gives this more context. But I want to talk about types. I would like to, oh, come on, Beach, we can do it. BI for the win. So this will be a quick exercise to determine the types of different variables. And this is something that helps when you're deciding, like, hey, should I use the address of, or should I use a dereference, or what do I need to return from this function? So we're going to try a few of these things. And it's different coming from a language like JavaScript, where it's very loosely typed, where JavaScript is more than happy to do things like add a string to a number. You know, it has some behavior there, but if in C, if you try to do that, it complains. Even in Python, it complains, right? If you try to add a string to a number. So, but C is very strongly typed. It's sort of the opposite of JavaScript in that way. And so you always need to be cognizant of what type something is. And usually that's pretty straightforward with numbers, but when you start getting into pointers, then it gets a little bit different. So here's how this exercise works. If we make a variable like int a, we need to be able to say what type this is. This is an int. But it's not just the variables. Pointer to an int, or int pointer, however you want to say it. It's expressions too. So if I give this expression right here, which does nothing in C, but it's a valid C expression, this whole expression has a type, and that type is int because a is an int. Likewise, this expression has a type. It's also int because that result is an int. C does some conversions for you automatically. Like this is a floating point number, and if we add that to an integer, then the result of the entire expression is a float. So does this make sense where I'm going here? We've got the types of the variables as we've declared them, and then we have types of expressions that exist. So if I say printf %d and then we say a times 4, then this little sub-expression right here, a times 4, that has a type. The result of that expression, once it's evaluated, that result has a type. In C, every expression that gets evaluated has a type. So what would be the type of this sub-expression, a times 4, that I have highlighted? What is the type of the result of that calculation is another way of asking that question. It's also an int. Yeah, so that sub-expression is an int. Now, virtually everything in C, when you get out here in the core of your program, is an expression. So I could also ask you, what type is this expression? The whole line, printf, all that stuff. A times 4 is kind of what we call a sub-expression within that expression. But the whole line itself is an expression that has a type. How would we figure out what type that was? Or again, asking it a slightly different way, once this expression is evaluated, what type is the result? How could we find that out? Kind of weird, because you're like, printf? Printf outputs stuff to the screen. Like, how does it have a type? And I swear this will get to pointers. Let me ask a slightly different question. What is the type of this whole expression? How could we figure that out? There is... Seems like type of is something I've not used in ages. Check the return value. I'm gonna have to look at type of again. Yeah, so the question again is, what is the type of this expression? And that's the same as asking, what is the type of the result of this expression? So after the whole expression is evaluated, what is the type of the result? And if we look over at the man page for square root, it'll tell us what the return value is. It'll actually tell us the return type where? Right here. Because in C, right, when you declare a function, the return type is what comes before the name of the function. So it's a double. Square root says it returns a double, which is a floating point number. It's like a double precision floating point number. So that is the whole type of this. The type of this expression is double. So what's the type of the printf? Let's do the same thing. Man3 printf. The return type is int. A lot of people don't realize that printf actually returns something, and usually it's just ignored, right? Upon successful return, these functions return the number of characters printed. All right. So the type of this expression is int. All right. So those are the rules of the game. Determine what type something is. And it's floats and ints is one thing, but when we start getting to pointers, now things get interesting. All right. I'll shrink this up a little bit. Oops, value. And let's do some pointer stuff. All right, we already said that A is an int. What type is this? The address of A. By the way, this stuff will actually compile, assuming we were in a function, of course. These lines that just have single expressions on them like that. But they have no effect. Pointer to an int. Remember, the address of a variable is the same as saying a pointer to a variable. So yeah, this expression right here has type pointer to an int. Let that sink in for a second. Let's do a flip side one. We see p up here as a pointer to an integer. So what type is this expression? Not a trick question. It's an int pointer. What type is this expression? Dereference p. So remember, ampersand, the address of it takes a thing and returns a pointer to that thing, whereas dereference does the opposite. It takes a pointer to a thing and returns the thing. Yeah, it's just an integer. It's whatever p is pointing at. So you can kind of see here how the ampersand changes something into a pointer, and the dereference changes it away from being the pointer. So I don't remember who it was yesterday who said that ampersand and asterisk are kind of opposites of one another. One of them gives a pointer to a thing to you, and one of them gives the thing from the pointer itself. Here's a funky one. What type is that? Use what we have up there, line 14 and 15 with A as a hint. Taking the address of gives you a pointer to the thing. That's exactly it. Type int pointer pointer. Pointer to a pointer to an int. Pointers to pointers do come up occasionally. I don't know that we use them in any of the exercises this week, but there's a takeaway here that is P is just a regular old variable. A is a regular old variable, right, that holds integers. P is a regular old variable that holds pointers to integers. Remember, a pointer is just an index, it's just a number. So P is just a variable, it just happens to be a number that points to a thing. And you can always have pointers to variables, and since P is a variable, you can have a pointer to P if you want. You totally can. You can have pointers to pointers to pointers. The only case I know of that commonly comes up, and even that's not that common, is if you have an n-dimensional matrix and you want to dynamically allocate that with malloc. So if you have like a 3 or a 4-dimensional array and you want to dynamically allocate that entire array, then you have a number, you have pointers to pointers to pointers, depending on how many dimensions that array is. So a 1-dimensional array, you can just use a pointer. But a 2-dimensional array, you'll need a pointer to some pointers. 3-dimensional array, you'll need pointers to pointers to pointers, and so on. That's if you want to dynamically allocate them. You don't know what the size is ahead of time. Another common place a pointer to a pointer is used, I can probably demonstrate in a little bit, but we'll save that. It's very similar to what we did yesterday, where we had a function where you passed a pointer to an int in there, and then the function changed the value of that int from within the function. Sometimes some functions want to change the value of a pointer. They want to change what the pointer is pointing at. And if a function needs to change a variable that exists out in the caller, then that function needs a pointer to that thing so that it can change it on its own. So that's another case where pointers to pointers may come into play if the function itself needs to change what the pointer is pointing, or what address the pointer is pointing at, to change it to point to something different. With a regular pointer, you can change what it's pointing at. You can change the value that it's pointing at, I should say. But if you have a pointer to a pointer, you can change it to point to something completely different. So let's make a Q type here. And so I can do an assignment like this. Because how does this work? We know that the right-hand side is a pointer to an int, and we know the left-hand side of this assignment is a pointer to an int. And if you're doing an assignment, both the left-hand side and right-hand side have to be the same type when you're dealing with pointers. So this assignment is okay. We've got pointer to int on both sides. We know this one's a pointer to an int because we just got it right there. Again, the takeaway here, ampersand changes it into a pointer, dereference changes it from a pointer. And then this assignment, it's important to note that the types on both sides of the equals are the same. If we were to do something like this, we would get an error. It's a type mismatch. We have an int pointer on the right and an int pointer on the left. So they need to both be the same type. Also, incidentally, the type of an assignment expression is the same as the left-hand side. So the type of this whole expression right here, this whole line, is pointer to int. How's everybody feeling? More questions. What type is this and this and this and this? Let's go with the first one. What type is Q? These get progressively harder. Q is a pointer to an int. We know right up there, line 7. We've declared it that way. What about this expression? We've dereferenced it, so we get rid of one of those asterisks. What about this one? Dereferenced it twice. Now we're down to int. What about this thing? Ooh. Pointer to an int. Good guess. Because we are got a dereference there. It is indeed an error. So we have the value of the int right here with the double dereference, but with the triple dereference, we can't do it. This would be like saying we have a variable x, and I want to know what dereference x is. You just simply can't dereference that because one does not simply dereference it. It's not a pointer, so you can't dereference it. So another way of thinking of it is if I put parentheses here, this sub-expression between the parentheses, we've already determined that's an int, and we're not allowed to dereference an int. So that's just going to be an error. We've dereferenced it one time too far. Well, let's see here. Yep, that's pretty much it, Thomas. So even a pointer to a pointer, that still just has a memory address in it, memory location in it, because it's a pointer. Anything that's a pointer, period, or a pointer to any other type, I should say, anything that's a pointer to any other type is a memory location, because pointers are memory locations. They're memory addresses. Indexes in a memory, the same thing. So yeah, so all of them have memory locations until we get to this expression, which is actually the value that's in one of those memory locations. It gets a little brain bending because all variables are stored in memory. So A is in memory somewhere, P is in memory somewhere, and Q is in memory somewhere. Remember, A just holds a number, and like viscerally, most people are pretty cool with understanding, oh, hey, yeah, we've got a number, so that's stored in memory somewhere. But then it's a little brain bendy to think, oh, well, P is stored in memory too? Doesn't P refer to memory? It does, yes. And it is also stored in memory itself. Because remember, memory addresses are just indexes, they're just numbers. So whatever we store in P has to be stored somewhere. So we store that number in memory as well, which is how we can have a pointer to P, because P is actually stored someplace in RAM. Same with Q. Q is stored someplace in RAM, even though it's a pointer to an int. That has a value. We had it, I think we have it pointing to P down later in the code, and P's address has to be stored in memory. So it's a little brain bending there. It's probably easier just to think of the usage for now and the way dereference and ampersand is used. Let's see. Can we use the syntax? The address of dereference P. Never mind. All right. We can use address of P to look at P's memory address. Address of dereference P would look at A's memory address. because dereference P is A. But remembering that memory is like an array, and each array elements have an index, and then they have the thing that's stored at that index. I had a thought that went along with that start of that sentence right there. It just kind of goes sometimes. Oh yes, what I was going to say. Some people like to think of this as buckets. So you have memories of just a whole line of buckets, and the buckets are numbered 0, 1, 2, 3, 4, 5, 6, 7, and so on. You can put numbers in the buckets and store them in the buckets. And so we could say like, hey, what's in bucket 12? And maybe the value of A is in bucket 12. And then we say what's in bucket 13? Maybe the value of P is in bucket 13. But P is a pointer to A, so its value is 12 because that's where A is. Let's draw some buckets. Let's see if that works. I'm going to use buckets 0 through 9 so that they fit in one column. So these are my addresses, which are arrays into our memory index. And let's say that A is at address 2, and P is here at address 8. And A has the value, what? 99. So these are our bucket numbers right here. 0 through 9. And A is in bucket number 2, and the value 99 is stored in bucket number 2, just like we have here. And then if we do something like this, let's do this. Use the address of A. Did I not do that yet? I don't think I did. So P gets assigned the address of A. And so initially the value of P here is garbage. Could be anything because we haven't initialized it yet. But if we say P is the address of A, then what value goes here? What do you guys think? 2. Yeah, I like 2 because 2 is the address of A. So we'll store that there. Let's add one more thing right here. I'm going to say the variable Q is at address 5. And the value that's there is initially garbage because we haven't assigned anything to it. But if we do Q is the address of P, because remember Q is a pointer to an int, what value goes here? 8, because that's where P is in memory. Right there. And so now, if we have this chain set up where Q is a pointer to P and P is a pointer to A, you can see how the compiler can figure out by doing a bunch of dereferences. If we ask for dereference P, for instance, it's going to look at the value that's stored here for P, which is 2. Then the dereference is going to cause it to bump over here to address 2 and look at the value that's there. Likewise, if we do double dereference Q, the same chain is going to be followed. We're going to look at what's stored here for Q, address 8. That's one of the dereferences. So we pop over here. We're going to look at what's stored in address 8, which is 2. That's the other one of the dereferences. So we pop over here to address 2, and we look and see what's stored in address 2. Oh. So while pointers are kind of mysterious, they're under the covers, they're actually just a regular variable like everybody else. They just store a value somewhere in memory. And doing dereferences is our way of traversing this chain of pointers. So somebody holds one person's address, you dereference to get to that person. That person holds another address, you dereference to get to that address. What do we think now? Was this, let me ask this question. This little diagram, was this clarifying or confusing? Let me put that up at a poll. Oops, that's not what I wanted. Add options. Clarifying. That's a pretty good run. Describing pointers is tough, and learning about pointers is tough. So I like to try all kinds of different things and see what works. All right, I'm gonna, whoops, don't write KKK there, Beej. In case you're curious, K is a cursor movement key in VI. So I'll show you another little trick right here. That J at the end of that line is extraneous. Sometimes C programmers comment out blocks of code using if zero, which is basically false, and then end if like this. You might see that occasionally in C code. It has the advantage of being able to block out comments like this that normally you couldn't comment around because you can't nest comments. But anyway, I'll put that there. I'm going to paste this thing in. Okay. Next, I wanted to talk about function syntax and pointers and returning pointers and stuff. But before I do, is there anything else on this block of code that we should talk about? Questions on any of this stuff? Or additional thoughts? I used a lot of int pointers here, but we could have used pointers to anything. I guess I want to reiterate, it's an important takeaway that when you're doing an assignment like this, that the left-hand side and right-hand side match up in terms of type. It's also a good takeaway to always kind of keep in the back of your mind what type an expression is while you're putting it in. It can save you pain on things like if you think that if you're hoping that this gives you a float answer, but you realize that both sides of that are integers, so C does an integer division, so it makes it an int results instead. So keeping types in mind and types of sub-expressions in mind helps. Admittedly, not so much with numeric types, but with pointers, definitely. Yeah, so how do you make this a float? So this is definitely an int right here. But if we wanted to make it a float, there are a couple different ways of doing it. three different ways that are coming to mind. If you wanted to force this to be a float, my personal favorite is to do this. And the right-hand side, or the 12.0, that's a float, so the whole thing becomes a float. I like that. You can also cast. That's probably less common. And then there's also a way to declare a floating constant like this. So, I don't know, kind of a matter of personal preference, I guess. You could also cast A to a float if you wanted. But there's a school of thought, whoa, VI fail. There's a school of thought that casting is ugly and that you should only cast when you absolutely have to, and there are only a few cases where you absolutely have to. And I don't frown on people when they cast, unless it's a cast that they really shouldn't be doing. But since this case has a couple other options that are visually quite appealing, I don't do a cast there. Uh, 12F always works, I think. Or does it? It's complaining about it. Do I have that wrong? Hang on a second. Is it capital F? What is it? Too many languages. No, it says lower. I'll get to that one in just a second, Vim. Let's see here. What are you asking about? Extra text after. I wonder if it's not part of the early standard. Suffix, if one is present, FF, floating point literal. I'm going to turn on all my warnings. Actually, I shouldn't do that because I'm already going to get a pile of warnings. Expression result unused. All these warnings are telling me that these lines do nothing. That it's computing A divided by 12, but it's not doing anything with it. So it's just throwing it away. What do we have here? Expression unused, expression unused. Ignoring return value. Invalid digit F. I wonder if it's part of a higher standard. Nope. I could have sworn this worked, but I could be mistaken. I'm gonna have to look up whatever I was thinking of. That's gonna drive me crazy. Let me see here. Maybe it's not in C99. Let me see what different standards we have. C90, 99. New 11. Nope. Still giving the errors. Maybe I dreamed it. It's definitely a C++ism, but I thought it had made it into the C standard somewhere. All right, I guess that's not a thing. It's blowing my mind because I swear I used it. Anyway, Okay. All right. Vim's question. Are all of these valid? This is a great question. I'm going to go ahead and blow away that stuff, and let's get rid of this stuff. All right. So what do we have here? We have it this way. Pointer A, int pointer A. This is a good question. Int A and int A pointer. All right. What do we got here? All right. I'm going to separate these into two groups. This is a good question. I've been typing this way the entire time, right? And this is saying A is a pointer to an int. Turns out this is the same thing. The compiler doesn't care if you do this or this. Now, I have an argument that this way is better. And I'll tell you why, and then we'll get to these guys later. And the rationale is this. If I type this, let's see, oops, C and D. These two lines are exactly the same. Different variable names, obviously, but the effect is exactly the same between these two lines. So the question is, the answer is going to be the same for both these lines. Let's do this one first. What type is E? Pointer to an int. And what type is F? F is just an int. Yep, just a plain old int. And I told you already the two answers for these lines are the same. Because it doesn't matter where the space is. But I argue that this line is less clear because it kind of looks like we're saying, hey, the type is int pointer, and C and D are both those types. But that's incorrect. As we see, C is type int pointer and D is type int. So I like writing it this way because that clarifies to me reading it that E is an int pointer clearly, F is just an int, and that's all. So two lines are the same. I prefer this one. And I'd argue that this one's probably more common. Does that make sense for those first two? Oh, what is the context? Let me answer that in a minute. Let's talk about this one first because this ties into that question again. So these two lines, they're both declarations. They're declaring variable A. And I know it's a declaration because it has the word int in here. And int is not in parentheses, so it's not a cast. But this is like we're declaring a variable, right? So it turns out when you're declaring a pointer variable, the only place you can have that asterisk is in the middle, or rather before the variable, I should say. So having the asterisk afterwards in a declaration doesn't work, and having it before the int in a declaration, again, I'm being extra clear here that we are in the context of making a declaration of a variable at this point, as opposed to out in some runnable code that's doing things. At this point, we're just saying, hey, I got this variable A, and here's the type. But our options for doing a type of A are having an asterisk before it, either there or here, the way I don't like it, or not having an asterisk at all. These are our options for declaring A. And the first two declare it as a pointer to an int. The last one declares it as an int. But putting the asterisk afterwards is a syntax error, and putting it before the int is also a syntax error. Of course, this won't compile because we're redefining A all over the place, but that's okay. Can we do lines 10 and 11 if not with the declarations? Yeah, kind of. Depends. Let's see here. How should I do this? So again, this code isn't going to compile because we're redefining A all over the place. I'm just using it sort of as an example here. So if A is a pointer to an int, let me put a comment to that effect, or just I'll make a new variable here. What haven't I used? B, int pointer B. So if B is a pointer to an int, then this is valid because we're dereferencing B. And we're not in a declaration here. We're in some code at this point. Like we saw before, if we do this, it's an error because it's too many dereferences. So you can put the leading asterisk here as a dereference. Trailing asterisk is different. It doesn't have any meaning in the pointer context. So this is just a syntax error. Actually, A, C, D, E, F, G. I'm going to make a G. And it's also a syntax error with a pointer. But what the compiler is thinking at this point is that you're probably wanting to multiply. It's like, oh, you're probably going in that direction. So that's the context that, in this context, we've got to multiply all of a sudden, as opposed to this. There's no pointer multiplication. So if you did this, then that's an error. Mouse pointer. Oh, everything is so sluggish while Zoom is recording. I took out the main because that won't compile in any case. Were there any follow-up questions to this stuff? What we just did here? Anything confusing out of that? Again, the big takeaway, I think, is be mindful of the context that we're in. Are we in a declaration? If we are, then the asterisk means one thing. If we're not in a declaration, we're out in our code, asterisk means something else. If we're in the declaration, the asterisk means we're declaring a type that is a pointer to something. But out in the main code, asterisk means all kinds of stuff. If it's before a pointer, that means we're dereferencing that pointer. If it's between two integer variables, it means we're multiplying them together. Well, let's see, line 24, can we do dereference b times 2? Yeah, we totally can. Dereference b times 2, this is fine. And, okay, because it's fine because b, let's see, dereference b is an int, right? B is an int pointer, dereference b is an int, and so the result of this sub-expression right here, dereference b, is integer, and in C, we're totally fine doing an integer multiplied times another integer. So yeah, that totally works. I think so. I think that should be fine. And we're having a question that's coming up is kind of a order of operations. Like what happens first in this expression? That is, the question is, does the expression evaluate like this? Or does the expression evaluate like this? Where are the implied parentheses in this expression? And it's the same question if we have spaces around here, by the way. Where do the parentheses go? Does the dereference happen first? Or does the multiply happen first? Is this a problem? Is this similar to any problems you guys have seen in JavaScript or in the past? Out of curiosity? And how could we figure out which of these, does it do this? Or does it do this one? Parentheses definitely do. So yeah, I should rephrase the question so it's not as confusing. If we do parentheses here, then b times 2 will definitely happen first. And if we do parentheses here, dereference b will definitely happen first. But the question is on this line right here, which does it behave like? Does it behave like this one? Or does it behave like that one? Yeah, the second one definitely goes first. Left to right, that's a good assumption. But the details are actually a little more nuanced. For instance, if I have this expression, actually this probably better be something different. We're pretty used to the rules of math that multiply happens first, right? So first we do 5 times 3 is 15, then we do 2 times 4 is 8, and then we add 15 and 8 and get 23. But if we just went left to right, we would do 5 times 3 is 15, plus 2 is 17, times 4 is whatever that is, 68. So there are some implied rules here. So if we write this expression down, the implication is that this is what's happening. So there are some rules that are hidden away. These rules are called the rules of operator precedence. And so if I go up here and I say, what is the C operator precedence? We're going to get a reference somewhere. And operator precedence is a thing that exists in all languages. And the higher the precedence, the sooner it gets evaluated. And so where's our multiply and stuff? Let's use the size of plus minus. Here we go. So precedence 3, we have multiply, divide, and mod. Precedence 4, we have plus and minus. This means that the multiplies are going to happen first because they're precedence 3 as opposed to precedence 4 for plus and minus, which will happen later, which is why in our code here, why on this line, the multiplies happen first because they have higher precedence. So there are rules for all these things. So here we have a dereference and a multiply. The question is, what has higher precedence, the dereference or the multiply? So we can go pop back to the table here and we can have a look. We already saw the multiply was here. And up here, we see asterisk for indirection, dereference. So the dereference has higher precedence. So it happens first. So just like you guys found when you tried it out, this is the one that happens. The implied parentheses are around the dereference because it has higher precedence. Oh, now you're going to trap me with precedence questions. It's totally possible to write ambiguous expressions in C, and I don't know them all off the top of my head. If you've got this thing, you can write expressions like, what's a good one? X plus y, like pre-increment y, and if you take out all the spaces, you end up with that, but that's ambiguous. Right? Did you mean this? Or did you mean this? So it's possible to have ambiguous things. I'm pretty sure 2 times dereference B is going to go that way, but I'm not 100% positive. As a developer, when in doubt, just put parentheses in. Like, the worst thing that's going to happen is they're going to be extraneous, but somebody reading your code in the future will probably thank you if you have something that's weird, like 2 times dereference B. Like, put parentheses around the dereference B, and doesn't harm anything, makes the code more readable. I'm pretty sure the compiler can figure out 2 asterisk asterisk B. I'm pretty sure it can figure that one out. The plus 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 one, it can't. But yeah, there's an argument that we made that's totally valid, that more readable code is worth something, so that a future developer coming along can figure out what's going on without looking at 2 star star B and going, ah. It's no problem for me to entertain these. I find them entertaining. All right. Oh, let's see. Oh, yeah. Yes. So this has to do with something that I don't know how much I want to talk about, but I think they're definitely called promotions. Let's see. Implicit type promotion rules. Let's see if Stack Overflow does this for us. So it's kind of more than I want to talk about, but C will automatically promote a type like char to a higher type like integer in certain cases. And it has to do with this rank, and the spec is really nasty. Let's see here. If an int can represent all values of the original type, the value is converted to an int. Otherwise, it's converted to an unsigned int. So it's, I guess the shortest, simplest answer is that when you pass a char into a function, that char gets converted into an integer when it arrives at the function. It's totally possible to have a function that accepts a char value as well. And I'm not actually sure if it gets converted from a char to an int and back again. It probably does. But the upshot is when you call these functions with chars, the compiler promotes that char to an integer. And that's why all the string functions that we have, let's see here, like stir. No, actually, let's use strchar, because that actually it takes a character as an argument, and we see here it's an integer because it's been promoted to that. So I don't want to dive into that too much. If you want to learn more about it, look up integer promotions and see. Just take it as read that if you pass a char into a function, it gets promoted to an integer. And that's fine because the integer is capable of representing all char values. So it doesn't harm anything. Let's see, important to know the difference between signed and unsigned types. Yeah, but let's talk about that more when we get to computer architecture. For now, it's good enough to know that signed types can represent negative numbers and positive numbers, and unsigned types can only represent positive numbers. Yeah, that should work out just fine. It should work out fine if it's char in the caller, and it should also actually work out fine if you declare the function with char up here instead of int. Yeah, Thomas points out that the unsigned types can hold numbers of larger magnitude. So like a signed char can only hold up to 128, I think, as the largest positive number. But an unsigned char can hold up to 255 as the largest positive number. So kind of different ranges there. Oh, you know what? I have a wiki page on this. Where is it? That's signed and unsigned. All right, here you go. If you want to see more about how signed and unsigned numbers work, there is a page in the wiki. Default is signed. If you just say int, it's a signed int. And then I'm going to put a little asterisk there because we're in asterisk mode. Char is a little bit different. It doesn't have a specified default, whether char is signed or unsigned. Unbelievably, in the spec, it turns out it's up to the implementation. If you just say char, it might be signed, it might be unsigned. If you want one for sure, then be explicit and say, this is a type unsigned char. But for all the other ones, if you just say int, that's a signed int. If you say unsigned int, that's an unsigned int. But I digress. We will talk more about this in architecture, I think. But we're over time for a break. Let's do a 5-minute break, and then we can come back and talk about some string manipulation functions, if that sounds good. And I can get more tea because my space tea is woefully empty. My stomach's already growling. Too early for lunch. All right, everybody coffee up, and then we'll polish off the hour, talk about some string manipulation functions. Oh, I should hit start. Be right back. All right. Everybody got their hot drinks. This fall weather setting in. Totally craving beef stew. Get up early and put it all in the slow cooker and have it done for dinner. Oh. I guess maybe it's only fall weather for those of us this far north. Does anybody live in the Northeast? Nobody? Is everybody back from break? Seems not. I hear fall is awesome there. Always haven't been on my list to go see. Here in the desert, we get some color, but that's nothing like over there. Oh, all right. Any questions come up during break I can answer? Otherwise, I was going to launch into some sample string manipulation functions. Maybe I had an idea for a fun little program here. Mr. Copy, Mr. Lin. All right, if nothing else, let's hack together something. Let's see, find string. What are we doing? Swap, find character, string copy, string compare, and find. All right, so we're not doing length. Let's do a string length function here. I have to call it string length because there's already strlen. There's going to be additional stuff on Thursday, Friday. So if you finish the stuff that is in this repo today, then you are on track. That said, the stuff Thursday, Friday isn't nearly as intense. So even if you don't finish the stuff today, keep working on it. And the Thursday, Friday's repo is got some different stuff. It's more like applied C in an operating system context. But it doesn't have as much of like, holy cow, we have to learn this whole language right now in it. Oh, you did string length in the strings folder of your project. Oh, that's right. Did you? I thought I was looking at strings. Well, then string length is a bad one. And we had a find character thing. I'll do a variant of find character. Let's do a function that, let's do two things. Let's do a function that converts a string into a decimal number. So if I give you a string that's like 124, that would return an integer 124. So this will be a string to decimal conversion. Let's do that instead if you already did string length. String to int. And then I'm going to give it a string such as 124, and this should return an integer 124 that we can print out with %d. So let's write that, and we'll use some pointers to make that happen. Does that sound like a plan? And then I have a follow-up on it that will use pointers to pointers. Oh. If that sounds bad, stop me before I go too far. All right, I'm going to tell you guys the algorithm for this, so we don't have to think about the algorithm for converting a number into, or a string into a number. But the basic idea I'm going to add one more digit here just for fun. The basic idea is that we're going to keep an integer variable that's keeping a running total of what these numbers are. So the first iteration of our loop, A will start off to be 0. A is going to be our running total. And we're going to say add 1, because that's the first digit here. And then we're going to multiply by 10. And then we're going to add 2, because that's the second digit of 1, 2, 4, 5. And then we're going to multiply by 10, and so on. Add 4, and then add 5. Actually, I'm sorry, I'm going to change this around a little bit. First, we're going to multiply by 10, then we're going to add. That fixes my algorithm. There we go. So if we run this algorithm right here, this sequence of steps, A starts off as 0, and so I'm going to keep the running total here. 10 times 0 is still 0. 0 plus 1 is 1, times 10 is 10, plus 2 is 12, times 10 is 120, plus 4 is 124, times 10 is 1,240, plus 5 is 1,245. So this little algorithm can be used to take a sequence of digits like 1, 2, 4, 5, just like we have here. Take the sequence of digits and turn it into a number, 1,245. So that's the algorithm I'm going to implement right here. And we're going to try to do this with a pointer thing, with a pointer somehow. So there's our A equals 0 to start. And then I'm going to have some kind of loop. We'll choose a condition later for that. And in that loop, we're going to do A times equals 10, just like we did every time here. And then we're going to do A plus equals something to add the next character on. And at the end of the day, I want to return A. Oops. So this is going to be my algorithm to convert this string to an integer. But I've got some missing pieces here. We are 2 short expressions, sub-expressions even, away from having an algorithm that converts that string to an integer. What's the while condition going to be like? We want to do this while we have characters remaining. How do we know if we've run out of characters in the string? Actually, I'm missing another sub-expression here, aren't I? But that's okay. I'll dereference S. I like that. So this is shorthand for testing to see if S is not, or dereference S is not 0. So we could also lengthen it by saying, while it's not 0, or while it's not the character 0, which is all the same thing. So all those 3 things I just typed on this line are the same. C purists would probably keep it short like this. So while dereference S isn't 0, we multiply A times 10, and then we need to add on the individual characters. This one's got a little trippy thing that's going to throw you for a bit of a loop, but let's take a stab at it anyway. So the first character is what? Right here is 1. How do we get that first character? Using our pointer S. Just take a stab at it. And if it's right, it's right. And if it's not, then that's okay too. Dereference S. A plus equals dereference S. So that's going to look at the character, and we're going to end up with the character 1, and then we're going to add that to A. All right, what else am I missing here? What do I have to do with S? Oh, Nikki's looking ahead. We have to move S to the next one. Let's give this a run and see what happens. Include standard I/O for my printf, and let's really turn on warnings for this. All warnings and extra warnings. For the life of me, I never knew why all warnings didn't include extra warnings, but there we are. All right, no warnings at all. Let's give it a run, and we end up with 54,573, exactly what we're looking for. Wait a minute, that's not what we're looking for. We're looking for 1,245. Nikki was hinting at this. Dereference S is a char. And if we print out the values of those, let's just print it out along the way right here as a decimal number. I'll print out dereference S. That's going to print out a lot of numbers. We see 49, 50, 52, and 53, which probably does produce 54,573. But why am I getting 49 instead of 1? 49, what's that from? That's the ASCII value. It totally is. Let's look up our ASCII table again. It was ASCIItable.com. I forgot. The number 1 right here on this line. Oh, it's an image. Oh, look, he didn't even get it from it. He didn't even make it himself. He got it from lookuptables.com. Boo, I feel ripped off. Anyway, 1, the number 1 right here. If we look on the decimal side, 1 is 49, 2 is 50, and so on. Sure enough. All right, we're getting the ASCII code. Actually, I'm going to leave this up for a second. How can we go from the ASCII code? We see that 0 is 48, 1 is 49, 2 is 50. So at least they're in order, right? In ASCII, it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That runs from 48 straight up to 57. So what do I have to do if I've got 49 for 1? What do I have to do to this 49 to get down to 1? Subtract 48 from it. And in fact, this is the way in C to go from an ASCII number to a value. You subtract 48 from it. You'll notice that 48 here is the same as character 0. So back in our code, we can do exactly, I'll leave our printout in there. Dereference S minus 48. And I'll put dereference S minus 48 here in our run. So let's see if we get some good answer. So we got our good answer. So minus 48 is totally right. I'll go for I'll do the int thing in a second. It's a common idiom in C programming when you're doing exactly this thing. Instead of using 48, you use the character 0 instead. So these two lines are exactly equivalent because character 0, characters in single quotes, character 0 is equal to 48. Equivalent. Words and letters. So this one is more common, I think. But now we're actually getting our answer. 1, 2, 4, 5. Oh, we've converted a string into a value that we can now do math with. Mind you, you don't have to write this yourself. There is a function called stir to unsigned long. So there's already a function that does this. Takes a pointer to a string, and this function is actually a powerhouse. It does all kinds of stuff that our lame one doesn't do. It takes a pointer to the string that we want to convert, just like ours. It also takes a base, so you can convert it, the string, from like binary into a number or from hex to a number. It's also got this char pointer in it, interestingly. But before I go there, let's talk about casting to an int. Just like Thomas is pointing out. And the actual syntax would be, I'm going to comment this line out. We're going to break things a little bit. The actual syntax would be cast like this, if we were going to do that. So this is saying, hey, take dereference s and please cast that to a type integer. So this won't complain at all. But when we run it, we'll see we're back to our gigantic number. And if we take this line apart, this doesn't actually do that much. If we look at s, we know s is a pointer to a char. So the type of dereference s is what? If s is a char pointer, dereference s must be technically a char, but yeah, it's an integer value. Yeah, so exactly what you wrote there. So dereference s is 49. We cast that to an int, and it's like, okay, it's 49 as an integer now instead of a char, but it still remains 49 without doing that subtraction. So this is kind of one of those things in C where you're thinking probably this is an amazing amount of micromanagement that I've just had to do, like honestly, to convert a string into a number. Why did I have to do all this crazy stuff? I have to subtract 0 away from it? Like, The reason we have to do this is because C is such a low-level language that it's so very close to assembly language that if we looked at the assembly code that was generated for this, it would have these things in it. It would have this multiply by 10. It would have a subtract that thing off it. Because assembly code is certainly low level. It has no concept of conversions like this. So being only a step above assembly, we've got all this crazy hand-holding that takes place. And again, I'm going to put a note here. In real life, use stir to unsigned long instead, because it's going to be better than our little function here. I do have one more thing that I want to add to this. But before I do that, are there any questions about what we've done here? Particularly line 11, which is bumping S along that string. So we have that string 1, 2, 4, 5, and S starts by pointing here. And then every time we do S++, we're bumping it up to the next address. So then S points to the next one, and so on. And eventually, we've got that null character out at the end. And that's when this while statement, this while loop fails. And when it drops out. But the S++ is what's actually taking our pointer and bumping it along the string to the next character. Yeah. Stir to unsigned long. This is how that breaks up. String to unsigned long is what that means. I'm going to throw a challenge in here. This function is already returning an integer, but I want to know if we have any invalid characters in here. And I want to know where that invalid character is. What I'd like to get back, if we ran the function with this, I would like to get back the value that was parsable, 124. So I'd like to get 124 as a return value. But I also want to get a pointer to this position in the string. So s points inside our function, s will point to 1 because that's where it starts. But I also want to get back to the caller a pointer that points at this bad character. Whoa. So after this, I want to be able to print out the remainder of the string like this. And this should print x5, which is the remainder of the string starting with the bad character that was not parsable. But we're already returning a value. So we can't return the bad pointer. From yesterday, how do we get stuff back to the caller without returning it? Another parameter that's a pointer. So I'd like to pass in a pointer to my char pointer because I need my char pointer to change. Not just the thing it's pointing at. I don't need that to change at all. X is always going to be X. But I need the thing that it points to, the address that's stored within P. I need that to change. So I need to pass a pointer to P in here so that the function can change P. What type is this? Ampersand P. What type is that expression? If P is a char pointer, then ampersand P must be char pointer pointer. I'm going to put that in here. I'm going to call it bad for bad char here. All right. All right, so how do we detect if the character is bad? Say we're doing a conversion, just a straight decimal here. So next question would be like, how do we know that X is bad? 1, 2, 4, and 5 are good, but X is bad. What's our test for that? Less than 0, bigger than 9. Yeah. I'm going to add a new variable here. Just V for value. I'm going to say value is dereference S minus 0, just like we have on the next line. Whoa. So, and then I can change this to A plus equals V. So I'm just pulling this expression off that line to the next. And now we can do a test on there. Ampersand is address of, this one right here. Yeah. So this is the address of P, or also known as a pointer to P. So I pulled the value out here, and now we can do a test. If V is less than 0, or V is greater than 9, then we know we've got something bad, right? And now we just need to set our bad pointer to point at that. Ooh, so this is going to be a fun line to write. We already have a pointer that points at the bad character. Which one is that? Which variable is the pointer that's currently pointing at the bad character? S. S is bumping down the string. S started at 1, 2, 4, and so on. And eventually S, as it bounces down this string, it eventually lands here on X. And we determine that X is greater than 9, so we found a bad character. So we know that S points to the bad character at this point. Character. Am I just leaving characters off all over the place? But we want bad to also point to it. So we might be tempted to write this. S points to the bad character, and now bad must also point to the bad character. But I've made an error on this line. What have I done wrong? Different types. Tell me more. So the left-hand side, bad, is a pointer to a char pointer. The right-hand side is just a pointer to a char. So we have a type mismatch. So that's int pointer equals int pointer. That's a type mismatch right there. Bad is a pointer to a pointer. How do we get from the pointer to the pointer to just the pointer? That's right, we dereference it. This is just like we did before yesterday when we were changing the value in an integer. We were changing the value in the integer by dereferencing the pointer to the integer and putting a new value in there. We're doing the exact same thing here. We're putting a new value in the pointer by dereferencing the pointer to the pointer. And so we found a bad character here. I'm just going to go ahead and break at this point because I want to stop parsing right now. Like, we found a bad character, forget it. Wait a minute, do I have a bug here? I think I do. I think I'm going to end up with a value 10 times larger than what I want. So I'm going to move this times 10 down here. There we go. Cleaner code anyway. All right. Up here, figure out the value, test to make sure it's a good character. If it's a bad character, set the bad pointer, break out of the while loop, and then we should drop to the end of the function. So let's give this a shot. I'm hoping that it prints out 1, 2, 4 as our value, and then prints out x5 as the remainder of the string. Oh, unknown type S, what did I do? Oh, my little scratch paper up there causing syntax errors. All right. So we've successfully taken a pointer. We've passed a pointer to that pointer into this function. We had this function change the address that the pointer was pointing to. If you notice down here, we declared it, but we never initialized it. So it's pointing to garbage right now, which is probably a bad thing if we don't actually find a bad character. So I've got some problems with this code. If I do this and I run it, we've got P pointing to garbage. We never change it because we never found a bad character. So we should probably initialize P to something or make it a little bit better somehow or another. Let's see, what's one option for this? What if we always do this? Kind of thinking aloud now. We always set bad to point to whatever S is. Now if I run it, it points to the last character it found. That's not really useful. I don't know. There's some bug here that I'm not going to really deal with. The important takeaway is that I feel like I'm like one line away from it though. The important takeaway is that we could pass a pointer to a pointer and change the address that that pointer pointed to. Probably the most common use case of a pointer to a pointer right here is what we've done. And we saw it right here. There's end pointer that how does this, what's the quick way to make this work? It's driving me crazy. End pointer does the same thing as our bad pointer in string to unsigned log. They also have a little special case in here where you can pass null in here and it'll not do anything. It'll ignore the end pointer and not do anything with it. So in case you're not curious about where the bad character was. Anyway, I kind of want to fix this before I paste this into you guys. Any questions on this thing? Does that get me there? Ah, blast. There, I think that fixed it. Now I feel comfortable pasting it in. What do you guys think? Yeah, so it's just printing a blank line. The way I have it here is what happens is bad tracks along with S. As we're moving S along, the bad pointer tracks along with it. And if we find something bad, then we break out and bad just remains where it was. If we don't find something bad, then they both end up pointing at the null terminator at the end of the string. And so when I print it out here, it just prints nothing. Just a null terminator. We could do a test here to make sure that it is pointing at null. I will say, is dereference p equal to null? So a little Boolean expression here. This will be true. It'll be 1 if p is pointing at a null character. It'll be 0 if p is not pointing at a null character. So here it says 0, p is not pointing at a null character. Indeed, p is pointing at that x. But if we take our x out, then we see 1, it is pointing at a null character. So that's why it's just printing a blank line. It's printing out an empty string. Does that make sense? I believe that's how string to unsigned long works. That the end pointer will be, the value that it's pointing to will be null if it hasn't found any bad characters. You guys also witnessed some precedence ambiguity right here, where before I put these parentheses in, it was it was thinking it was going to do this, I think. Or what was it doing? Deruns bad plus plus. I can't. No, that doesn't make sense. What was it throwing away there? There was some ambiguity, though, that I had to do with this. So yeah, I think so. Yeah, I think, okay, yeah. So at first it did the, but now I'm forcing it to do the dereference first. So it did the dereference first. Oh, no, so it must have done the increment and then dereferenced it and then thrown it away. That makes sense. Okay, okay. Yeah, so if it was doing it this way instead because of the operator precedence, first it would increment our pointer to our pointer, then it would dereference it to get the pointer, and then it would do nothing. It would just throw that result away. But here I'm saying, like, no, actually get that pointer, dereference the pointer to give me the pointer, and then move that pointer. So if we I wonder if do we still have that precedence table up somewhere? I don't think we do. Let's have a look. They are the same precedence. So dereference is here, and oh wait, that's prefix. Oh, here's postfix. It's first. There we go. So prefix is when the plus plus comes before the thing, and postfix is when the plus plus comes after the thing. So we have plus plus afterwards here. So the plus plus happens first, then the dereference happens. It's kind of weird that the postfix is higher precedence than the prefix. And there's probably a language parsing design reason for that that I'm unaware of. I guess so. I seem to remember there's some horrible joke of an expression that makes use of plus and post increment and pre-increment and the unary plus, so that you just end up with this whole gigantic string of pluses in a row. I just don't remember what it is exactly. Anyway, so we've done all kinds of crazy stuff here. We've walked down the string with our pointer S, and we've converted that into a number using the algorithm for converting a string to a number, a character at a time. So we did that. But then we also had this pointer to a pointer where we actually changed the address that was stored in that pointer within the function and returned that value back out here to main. And again, note those similarities to what we did yesterday, where we had an integer and we wanted to change the value in that integer back in main. So we passed a pointer to the integer by using the address of, just like we're doing the address of here. This is another one of those cases where, even though it seems a little bit voodoo because we're using pointers, pointers themselves are just like any other ordinary variable. Pass a pointer to the thing, to the function, if you want that function to be able to modify that thing. All right, we're out of time for today. Any last minute questions or? Everybody's just ready to, everybody's brain is full at this point, I think. Ready to take a break for lunch? Oh yeah, totally. Trying to get to Q, yeah. The big mountain in between U and Q is, of course, quicksort. So keep hacking away on that stuff, and I will take a poll to see how far people have gotten at the end of the day here. I actually, this is one of my favorite algorithms, converting a string to a number, to a value. And it's really simple, but I just love the simplistic beauty of multiply the accumulated value by 10 and then add the next digit. Multiply it by 10, add the next digit. I just always thought that was so clean. And here, one more bonus thing. Hang on one second. There's one more command line flag I want to put in here. You can ignore what I'm doing right now. This is total bonus craziness that doesn't have anything to do with the assignment at all. Let's see, MASM Intel. I always forget this. Check this out. This is the assembly code that corresponds to that C program. So this is the assembly instructions that my x86 processor is going to run to actually run the program we just built. And I think, let's see, I'm going to maximize my screen here. Let's see, foo.c, foo.s. What do I want? I want this thing. And then I want to blow away this thing. See if we can find something in here that's, I got some strings here. Actually, I can't see you guys typing. Can you guys see my full screen when I have it on full screen? Yeah, all right, cool. So yeah, so here's some of our stuff, like that constant string 1245. Here's some of my %Ds and %Ss that got passed into printf. And we should be able to find main. Here's underscore main right here. Anything that starts with a period is like a assembler directive. I don't know what it does. The stuff that doesn't start with periods, these are assembly instructions themselves, like push, move, subtract. They all have special meanings. Load effective address means stuff in assembly world. Here's a call to string to int. So this is calling our function. Looks like we've set some stuff up and then we're calling our function. And then if we look up through the code, we're going to find string to int. It's right here. So here's our function. Some bookkeeping. We got this label, jump of equals. Here's a subtract. Subtract 48. Remember, we're subtracting 48 because that's the ASCII value for 0. So that got turned into this instruction. I do not see a multiply by 10 in here yet. Is there one? So you jump, jump, move. Sometimes they'll replace it with something faster. No, here it is. Integer multiply a bunch of stuff by 10. And then we add 1 onto it. So And then we've got a jump here, so our little loop is going, and here's our return from the end of the function, and so on. Just so you guys can see that there's, I know that the assembly code is Greek, and we're not actually going to talk about assembly code that much, even when we get to computer architecture. And x86 assembly code, what we were just looking at, is really hard to read. But we were able to kind of step in there and be like, oh, here's main, here's where it calls that function, here's where it multiplies by 10, and it's actually a pretty straightforward mapping between the C code that we wrote and the assembly code that got generated. So that was bonus material. You don't need to know anything about assembly to do the stuff that we're doing today, but I figured some of you might be stoked to see the actual code that the machine was running for the C code that got created. All right, any last minute questions before we do lunch? Oh, so for that compilation line, let me minimize this again. Let's come back to real world. You can still use this, I think. So what this is actually saying is it doesn't have anything to do with the chip. It has to do with the format of the assembly code. And there are two competing formats for assembly code. One's Intel and the other's AT&T. So if I rebuild this, we see that this code is subtly different. It's using like percent signs here and parentheses a little bit differently. So all it's doing is telling it what format we want the assembly code to be in. And I can read Intel format better than I can read AT&T format. So exact same program, exact same code, does the exact same thing, just written down in a slightly different dialect. That's all. I grew up with Intel dialect, so I know it. All right, gang. Everybody go grab some lunch. I'm not doing a burrito this time. I'm going to Safeway for a sandwich and a flu shot. Flu shots for lunch. All right, keep hacking away on that stuff. Keep those questions coming too. This is, I would love to make pointers as easy as possible. That's definitely my goal. But some things just can't be made really easy. It's like, what is the easiest way to climb Mount Everest? I guess helicopter. Even that's a little challenging. But I try to make it as easy as possible. But if you're finding it hard, don't feel bad. Everybody who learns pointers in C, everybody finds it hard. I found it very hard when I first learned it. So it's just tough stuff. But if you keep pushing on it, you will get a breakthrough in your mind. You're like, okay, I'm starting to see how this is coming together. And so keep pushing. It's the fight that makes you strong. All righty, gang. Video will get posted as always. Have a good lunch, and I'll talk to you soon.